In this video, we're going to go back and take another look at the ball drop data. And you might recall drawing scatter plots of this data as a homework problem. And most of your graphs were quite nice. And in your write-ups, most of you recognize that this is not, that there's a pattern in the data, or that it is a nonlinear pattern, or there's a slight curvature. There's different ways to say that. And basically what I'm talking about here is that as we move along from one point to the next, you can see there's actually a gentle curve, that if I were going to draw a straight line, there's no, these points are clearly not along a straight line. And so they're curving, which is really kind of a cool result. Now, one of the ideas that Newton is responsible for giving us, or formalizing, is the relationship between time that a distant, or that an object falls, and the distance that it's traveled. Now, this is a simplified version of the full distance formula, but this serves our purposes because the ball, when I dropped it, had an initial velocity of 0, and I'm considering its initial position to also be 0. So the 0 position was at the top of the scaffolding. So given those two simplifying assumptions, we have a formula that we can use that would predict the distance, or where the ball should be, or how far the ball should have fallen. And I thought, as a verification that all of the data were accurate, and my assumptions about how I collected the data were valid, I thought I should look at the positions of the ball, both in terms of what were observed and also what would be predicted. When I did that, I discovered something rather disturbing, that when I started to look at the data and time that I was using, I found that, like, even after 3 seconds, and I think the way I had the original data, it was more, the ball had fallen more than 3 seconds. Well, using Newton's equation, after 3 seconds, the ball should have fallen 144 feet. So that's obviously not correct. We've got a problem. And so what that caused me to do, and this is a good thing, this is kind of like how mathematical thinking works. We collect data, we make assumptions when we collect data, and then we use known equations, or well-established equations, to verify that our thinking is correct. So I started thinking about what could have went wrong. And one of the obvious things that came to mind was that I had misjudged, I was incorrect, I should say, about how many frames per second the camera was actually using. Because clearly, I believe Newton's equation is correct. I've used it before in physics classes, and I'm seeing it in real life with the data that I collected. So there's something that's not right here. And so I went back to the camera and I took another look, and what I realized was, instead of 30 frames per second, the camera was actually shooting 120 frames per second. So I needed to make an adjustment for that. Unfortunately, the adjustment was relatively simple, because I could just divide all my times by 4. Basically, I had overestimated the time that it took the ball to drop the 17.5 feet. I had overestimated that by about 4 times. So when I did that, I recalculated, and again, the red dots here are the actual distances, and the blue dots are the predicted distances. So definitely was on the right track here. And I know that this was absolutely a correct adjustment, because the camera, I could look on the camera and see I had misread the frames per second. So this is a better fit now. Yet the points still are not matching up quite right. You can see here that there's a pretty good gap here, and the gap is getting more extreme as we move up the curve. But all of these, let's see. these are all errors between the observed values and the predicted values. So there's still something not quite right here with the time. I'm quite confident about the positions, because those were photographed, and of course there's some error in the measure in seeing where the ball was at those time intervals. I'm also comfortable in the assumption that the time intervals are equal, because that's how the time lapse camera works. So that those things are all seeming reasonable to me. And what I realized when I went back and looked at the video is it was hard to tell. So I kind of set up my scaffolding kind of thing here again, just to draw a diagram. When I dropped the ball, it hung in the air for just briefly. When you actually, the clock really needs to start when the ball starts its movement downwards. And I realized that I had I had set 0 at the wrong place. In other words, the ball, when my hand lets go of the ball, the stopwatch starts. And so what I realized was that the ball had actually been falling longer than the way I had the original time interval set up. So I made that adjustment. And once I made those two adjustments, the observed values and the predicted values are lining up really well. So again, I'm not going to have you redraw the graph with the corrected time and values, because I think you get the idea. And you did discover the curvature, which was great. But for the purposes of doing the mathematical analysis, I really needed to have that, and especially what I'm going to do now, I really need to have that figured out. Now, one of the interesting things when we look at this graph, and it goes right back to the 17th century when Newton was looking at this, and even the 15th century when Galileo was thinking about these things. People generally didn't know or didn't really have any idea what the nature was of objects that fell. For example, the idea that the object would speed up, that wasn't anything that was widely understood or accepted even. But at the same time, when I look at this scatter plot, we can definitely see that the object speeding up. And one way to think about that is just thinking in terms of average speeds. So we can calculate, for example, if I pick a couple of points, if I pick this point and think about how long it's been falling, that's that distance from there to there, and then how far did it fall? Well, I can calculate the slope here, and this is basically what Newton was seeing when he started thinking about and discovering calculus, is this idea that, okay, I can connect those 2 points with a straight line, and if the velocity or the speed of the ball was constant, all of these line segments would have the same slope, meaning that their speeds are the same. And we can see from this graph, even though it's very, the ball hasn't been falling very long, and so these slopes aren't that much different, but they clearly are different. They clearly are different. In other words, the ball had fallen a further distance, is pretty clear, later on in the time than it did earlier. So this segment here is clearly shorter than the segment here, and we can even look at this most extreme example and see without a doubt that the slope of this line, and incidentally, these lines, we call these secant lines. Not that that's terribly important, but that's one idea that we could, just distinguishing with the vocabulary. Now, one of the things that I got interested in was what these actual average speeds were. So I just created a simple table, and all I did was, for this cell, this first column, I should say, I calculated the what I'm calling delta time, or the change in time from one time interval to the next. And notice that these are all pretty much the same value here. They are all the same value except for the first and last ones, and they're off by just a little teeny bit there. But that's because of the time lapse on the camera. So the change in time was constant from one picture to the next picture on the camera. The distances, though, that it fell, the next value I have, or the next column I hear, is the change. This is the change in distance, or in how far the ball fell over each time interval. Now, we hopefully everybody, or I mean, this is fairly well known that the idea of speed. Those of us that have driven cars or ridden in cars, we can look at the speedometer, for example, and see how fast the car is going, and that speed is miles per hour. So speed is distance per unit time. So what I have in this column, this last column, are the average speeds. I thought it was really interesting because you can see the acceleration. And now, when an object's accelerating, it means the distance it travels over each time interval increases. And we can see that increasing distance. And therefore, the speed is increasing. And this number right here jumped out at me, this very last number. And it kind of motivated me to think about an interesting question. Now, this is essentially the average speed of the ball over the interval between when it hit the ground and basically 8 or 9 hundredths of a second before it hit the ground. So this should be really close to the speed of the ball when it hit the ground. Now, if we use some modern calculus on the equation governing the distance the ball fell, what we find is 32 feet per second is pretty much about 33 feet per second. We're going to do the math on that in a couple of minutes, but about 33 feet per second is the number that the model that Newton came up with would predict. So we're real close to that speed, which we should be, because the predicted distances and the observed distances are the same. But these are all based on the observed distances. So I dropped the ball. You saw the video. I took estimated positions as it fell, and so empirically, which means from measurement, I have estimated the ball's speed when it hit the ground to be about 32 feet per second. That's moving pretty quickly too, as we'll find out in a few minutes here. But there's a distinction here, because I actually haven't calculated the speed when the ball hit the ground. What I calculated was the speed between an instant just before the ball hit the ground and the instant when it hit the ground. And in a way, this number is what we would call an infinitesimal. And this gets back to the idea of the 15th, 16th century, and even going back into the Greek ancient mathematicians, Aristotle and people like that, who were talking about this idea of infinitesimal. And that's been a focus of the study in this course up to this point. We've talked about Zeno's paradox and getting closer and closer to something, but never quite getting there, getting so close it's an infinitesimal distance. It's just such a small amount of time or distance, in this case time. So we're close, we know, but we don't have that exact number. So what I did was, let's see. Oh, so again, that's what I was describing a minute ago here, is this idea that this is a change in time. We would call it delta. Sometimes we refer to change as delta. in mathematics and in physics. I want to change the pen color here because we can't quite see what I'm circling. So this number here, this is the time, that the change in time from like the ball's position 8/10ths of a second, or 8/100ths, 8 or 9 hundredths of a second. And we could even think of it, we could round this to 0.1 just to make it easier to talk about. It's approximately about 1/10th of a second. So the average speed of the ball between 1/10th of a second before it hit the ground and when it hit the ground is about 32 feet per second. But that's not the speed when it hit the ground. The speed when it hit the ground we're going to refer to as the instantaneous velocity. And there's a distinction there, and that's something that Newton was really obsessed with. So what we're looking for is what we call the instantaneous velocity. And I'm going to actually refer to it as speed. Velocity and speed are very similar, though the difference is velocity can be positive or negative. So you can have an object, moving up or down or forward or backwards, and the sign plus or minus would indicate a direction. Speed is always positive, though. We call it the magnitude of the velocity. So you can be going, 100 miles an hour backwards. Technically, your velocity relative to the coordinate system you're measuring it in is negative. But again, we're really focused on how fast the ball's going and its speed. That's what we're interested in. So we're just going to focus on speed. Now, one of the ideas to understand is this idea of deltas, or delta t. The delta time, I call that column, and the symbol I'm going to use is the Greek delta, and this is a Greek letter, and in physics and mathematics, delta, and in chemistry and most of science, that delta symbol means change in. So what we're going to do is, or one idea that we can think about, I'm going to go back to this other graph here for a minute. Now, if I carefully sketch, let's see if I can sketch a couple of line segments here to illustrate this idea. I'm going to focus in on just a half a second for the time being, for the purposes of this graph or this presentation, and then we'll move on and talk about how to calculate the instantaneous speed when the ball hit the ground. What I'm doing is I'm carefully drawing a couple of line segments here. I'm drawing, or not line segments, secant lines. I'm trying to be really careful here because they're slightly different in slope. They're slightly different in slope, but they're close to each other. So the speed from the average speed from this point to this point and this point to this point are pretty much the same. Now we can zoom in on that even closer, and this is zoomed in on the same graph. And now we're going every hundredth of a second. And notice this really, at this point, as we zoom in here and look at, oops, not laser pointer. I didn't even know PowerPoint would do that. Pen. Yeah, so remember we're looking for the speed right at half a second into the ball's fall, and when we zoom in like this, notice it's just these points now are looking like they're really basically the same line, or the same line can connect those 3 points. And so the idea is that as we let that time interval shrink, get closer to zero, and right now the delta t we're talking about from right here to right here, delta t is 0.01, That's 0.5 minus 0.49. So we're looking at time intervals of 1/100th of a second. And if we average these two slopes together, we'd be real close to the instantaneous speed. But again, if you go back and you think about what was really perplexing Zeno and perplexing mathematicians throughout history, all the way up until Newton finally, and Leibniz as well, resolved this issue, is we can't tell from this analysis that what the ball's actual speed is at an instant in time. So we're going to do some calculus now to figure this out. And it will get fairly complicated, and so I'm not expecting everyone to be able to reproduce this. It's really for illustrative purposes. So what we know, make a note here. So using calculus. One of the things that Newton figured out was that the distance as a function of t is equal to 16, or not 16. No, I'm sorry, it is 16. 16 t squared and this is the equation that I used to create the predicted values in the previous scatter plot. Now we're going to call delta t is going to be the change in time. And so, as we saw from the previous table, the average velocity would be the slope of one of the secant lines. And the idea here is that this would be, we can think about this as the distance at time t plus delta t minus the distance at time t divided by the delta t we're talking about. Now, I'm going to be more specific here. This is, again, looking very abstract. I understand that. But what we're going to do is we're going to think about, what I want to do is think about the time. Now I'm going to come over here. And when did the ball hit the ground? Or actually, instead of that question, let me say, how long did it take the ball to hit the ground? How many seconds did the ball fall? My estimate for this is 1.0458 seconds. What that means is this average velocity equation is equal to 16 times that t value, which is 1.0458, plus that next little time interval. That would be the next delta t, whatever it is. And again, in the last table, I had that delta t at 0.01. And then that's going to be times, oops, and I need a square. Let me put the square because I'm using this formula. And then that'll be subtracted. I'll subtract off of that 16 times 1.0458 squared. And this whole thing's going to get divided by delta t. So whatever delta t is, this formula would give the average velocity for that time interval. But again, we're looking for the instantaneous velocity. And so I'm calling it velocity. I said I was going to call it speed. It's funny. Um, those I'm so used to just referring to velocity. Well, I guess I'll stick with velocity now. The instantaneous velocity. Now, basically, to figure out what the instantaneous velocity is, or another way to think about the instantaneous velocity is that's the velocity when delta t is actually equal to zero. But the problem is if we replace delta t with zero just directly in this formula, we'll end up with this zero in the denominator, which is not defined mathematically. Division by zero is not defined, and so this is an issue. Now, the big breakthrough was to think in terms of infinitesimals. And now we have this modern idea of limit. And so in calculus, we would say, well, the instantaneous velocity is the limit as t approaches zero of 16 times 1.0458 plus t delta t squared, etc. Incidentally, this equation has a name, this form. It's called the difference expression or difference equation, since I have it equal to instantaneous velocity here. So if you were to decide to to venture into the world of calculus, of course, there are a lot of prerequisites such as algebra and trigonometry to take, but it's a very interesting subject without a doubt. Anyone can learn calculus. There's no doubt in my mind about that if they choose. Now, this is a polynomial here. And again, if you've had algebra, I'll just write this up here. So I just want to it's actually called a quadratic, and I believe that there are students out there that have seen the quadratic before. But basically, what we have here is something like I'm just going to write it as t plus delta t squared, and this could be written in algebra. A lot of times you might see this as like a plus b squared as a quadratic or something like that, or even x plus y squared. There's different ways that it gets written, but it is a quadratic, and it's something that some students study. So let's see if I'm not going to go through the foiling. You may, the word foil may bring back memories of algebra for those that have had it at some point in their lives. But what I'm going to do is I am just going to do the FOIL of this polynomial. I almost said polynomial. It's hard to talk and do complicated mathematics. Oh, I lost my 4 here. Shoot, there's a 4 right there. 4.4058 squared. Now all of this is being divided by the delta t squared. Now there's a magical thing that happens when we expand that polynomial. Here's a subtraction sign. This term, I'm going to change colors here real quick to illustrate this. This term minus this term is 0 because they're opposites. 16 times 1.0458 squared minus 16 times 1.058 squared, that adds to 0. It's a major simplification. It's a major simplification because now when I go to the next line, what I'm going to see is the delta t's in the numerator and the denominator cancel with each other, which is a really nice thing. So 2 times 16 is 32, so I'll just simplify that. Oh, there's no square on that. Wish I had a way to erase that. Oh my goodness, but I forgot my delta t. See that? I was talking too much. There should be a delta t here when you FOIL that out. Sorry about that. And then that's plus a delta t squared. So this should have been 216, 1.0458 times delta t. Okay, that's all correct now. And notice there's a delta t here and a delta t here, and so those delta t's cancel. There's still one going to be left here because of this exponent, or this square. And again, my interest here isn't to try to teach you how to do this algebra. It's more just to illustrate how we would do this in calculus and what we would end up with. Oops, I didn't need that line. So this is going to be 32 times, actually, I'm making a mess right now. Let me just write it over here. So this is going to be the limit as delta t goes to 0, and the delta t's cancel here and here and over here, so we end up with the limit of 32 times 1.458 plus delta t. And since delta t is going to 0, this delta t is going to 0, the limit is equal to 32 times 1. Oh man, I lost my 0 here too. 0 there, 0 there. Okay. Yeah, see, this is my problem. I'm trying to talk and write. This should have been 0.4 here. This is actually why mathematicians don't do these things with numbers. I'm going to do this over again. I'm going to illustrate why mathematicians like to use symbols. So we can look at this same thing again by just using the t. This is 16t squared. So the velocity at time t is equal to the limit as delta t goes to 0 of 16 times t plus delta t squared minus 16 times delta t, or I'm sorry, 16 times t divided by delta t. That's a t. And then we have the limit. So delta t goes to 0. That's going to be 16t squared plus 2 times 16 t delta t plus delta t squared minus 16 delta t. Oh, no, 16t squared divided by delta t. There's no delta there. I guess I'm not doing much better with the symbols. Those guys subtract to 0. So we end up with 32t delta t plus delta t squared divided by delta t, which is the limit So what we find is the velocity at time t is equal to 32 times t. And that is actually a calculus result. And this is something called the derivative. There's actually a calculus and formula in calculus for taking the derivative. We would call this, my notation is a little bit unfortunate because we would, I called this dy of t. So if I called it y equal dy of t, this is a very common calculus kind of way to look at that. Then notationally, and this is Leibniz's notation, Leibniz would call this dy dx, and that's the differential that you saw in the video associated with this week's video on why Newton needed to invent calculus in the first place. The derivative dy dt is equal to 32t. So there we have it. And so if we want to find that velocity, the actual velocity when the ball hit the ground, that's at 1 point, look at my notes, 1.0458. It's going to equal 16 times 1 point, oh wait, I got that wrong, it's 32, not 16, 32 times, let me write that over. So the velocity at 1.0458 seconds of free fall is equal to 32 times 1.0458. And if we do the multiplication on our calculator, so 32 times 1.0458 tells us the ball is going about 33.4656 feet per second. And notice that's, it's a little bit faster than what the average velocity was over the 1/10 second before and when the ball hit. But we should expect the instantaneous velocity to be a bit faster because the ball was accelerating over. That's the whole point. That's what Newton was really trying to figure out. I mean, every small little time interval, the ball's continually accelerating. And so none of those average velocities will give us the actual velocity. Now, 32.5, roughly 32.5 feet per second. How fast is that? Feet per second, I don't have a good sense for. Miles per hour, I have a better sense for. And so for fun, I thought I'm going to calculate, I'm going to do a conversion and figure out how fast is the ball going in miles per hour. Oops. Because we all drive, or not all of us, but some of us ride in or drive cars, or many people have. So I have a better sense for that, those units, which is just a simple unit conversion. Well, I don't know how simple it is, but I'm just going to round this to 33.5 feet per 1 second. This is called unit analysis. This is a really nice technique for doing unit conversions. And so I want to get to miles per hour. So instead of feet here, I want miles. And I know in 1 mile, there are 5,280 feet. And this is, I guess, something, well, if I ever forget that, maybe I'll start to wonder if I'm losing my memory or something, because I've used this conversion many times in physics and other places over the years. And now I'm going to go from seconds to minutes. So I know there's 60 seconds in 1 minute. And the way I'm setting this up here is I want the minutes to be in the denominator. And see how the units cancel. The feet here cancel with the feet, and now we're in miles. The seconds here cancel with the seconds here, and the denominator's in minutes. But I want to be in hours, and there are 60 minutes in 1 hour. So one more 60 will cancel those minutes, and then we'll end up with miles per hour, which is what we're looking for. And when we do this on the calculator, let's see, I'm not sure. Let me try this, see if it works. All right, there's the calculator. So I'm going to take this 33.5 and divide it by 5,280 feet. And then multiply that by 60. And then multiply that by another 60. And what I find is that ball was going about 22.8 miles per hour. 22.8 miles per hour. And then I think when I was, before I became a math teacher at College of the Redwoods, and before I went to college, I used to work in a sheet metal shop locally in Eureka, actually. It was called Olson's Heating and Sheet Metal. It was my grandfather's and then my uncle's. But in any case, I used to install seamless gutter on houses, on the eaves. It was a horrible job for me because I'm afraid of heights. And it turns out when I look at this problem, it's a really good reason why I was afraid of heights, because that's a 17.5 foot fall. And if I would have fallen off of one of those tall ladders, say I was 17.5 feet on the ground, I'm no different than the ball. That was something that Galileo really pointed out. I mean, all objects accelerate at the same speed if you neglect things like air resistance and so forth, or accelerate at a constant rate, I should say. So anyway, I would have hit the ground at 22.8 miles per hour. That's pretty fast. That would hurt and break bones. So be careful when you're on ladders. That's kind of the moral of the story, I guess, or one of them. Now, I've also read that a 30-foot fall is a death fall. I mean, anything above 30, I think that's the red zone for, as again, I know some people have fallen out of airplanes and survived and stuff like that's happened. It's pretty unusual, though, for the most part. So in any case, out of curiosity, I just went back and I calculated how long it would take an object to fall 30 feet. Because I was curious. I read a book called Tall Trees, written by HSU professor Stephen Sillett. Very good book. And I believe I read the statistic in his book. In any case, I figured for to fall 30 feet, it takes 3.9 seconds. And so I can calculate the velocity at 1.369 seconds by using our now famous velocity equation. So I'm getting about 43.8 feet per second. And again, I'm curious about miles per hour. So I'm just going to do the same calculation as before. Divide this by the 5,280 to convert from feet to miles, and then I can multiply by 3,600. 60 times 60 is 3,600. A little shortcut. So that's about 29.9 miles per hour. So about 30 miles per hour, according to what I read in Stephen Sillett's book, would be fast enough to kill somebody, most humans. I haven't done any internet research on this, so it could be that this isn't correct, but that's just going from memory. That's fast. That's going to hurt though. And I worked on many ladders that were close to 30 feet off the ground. So now I went to college, I worked hard, and I became a math professor. So no more ladders for me. Okay, I hope you enjoyed this video, and please feel free to message me any questions that you have or anything you want to ask me about. So I'll see you next time.